gives you a somewhat easy section here. And like I say somewhat easy. Okay. So this is the only types of situations where actually graphing is what I do want you guys to know how to do. And that's functions of several variables. So in two variables, we use a notation y equals f of x. In dimensions of three variables, we use a notation z equals f of x plus f of y, right? Because it's represented as two with one variable involved, right? So as you guys go older, you know, go into multivariable differential equations, and theoretical, you can have 4, even 5, or infinite n values of this. You know, that's when things go like, how is that possible? Going to n space, we have, you know, 50 different types of dimensions. That's the crazy part, you know, thinking about kind of stuff as well, right? Anyways, but that's what we're gonna deal with. But for now, we're gonna go back to our everyday first 2D and 3D dimensions. So to make things in 2 dimensions, for example, x and y is always going to be independent, and z is going to be the dependent variable in our function. Okay, and that's usually the case, right? So if you go back to our basic xy plane, right, and you went way back to algebra, how do we graph normally? You always pick whatever you want for x, and therefore the y has to be fixed because you can't plug that in, right? You plug this in, and it's fixed y. Hence the reason why x is called an independent variable and y is called the dependent variable. Well, when we do in 3-dimensional space, same thing applies. However, now we have 2 independent variables, which is x and y, and the dependent variable is going to be z. And that template goes on for 4 dimensions, 5 dimensions, and 6 dimensions, and things like that. So little multi-variable integration there. You go into 4 and 5 stuff. However, the first part of this section is pretty straightforward. It just gives you a little practice of notation. So going back to function notation, which is everybody's favorite. So given f of x, we want to find f of 1, 0 for each function. So, right, this represents x and y. So all we're really going to do is just plug in the numbers where they're supposed to be and see what we get. What's our output, right? So what's the z value going to be? Can't get any easier than that. So plug in 0 and 1 everywhere I see x and 1 respectively. So that just gives us a nice, beautiful 4. Do the same thing over here. Gives us this. And this is the one thing you got to be very careful of, because natural log of 1 is actually 0. So 1 times 0 is still 0. But you know, that's no fun, right? That's too easy. So let's get something more difficult. Now, the good thing is we can actually graph or sketch curves based off that information we just did, just plugging in numbers. And this goes off here. So sketching graphs for fun. I say that, you know, ironically, right? Graphing isn't always fun in general. However, how we're going to graph to make it a lot more fun is we're always going to be graphing the intercepts. That means the x, y, and z intercepts. And just in case you guys forgot, right, the x and y intercepts look like this. Meaning we plug 0 in for 2 of them and solve for the other variable we need for. And that's a nice thing, is that's a quick way of sketching in 3 dimensions. Well, some functions or some solids, let's just say. Okay. So let's do exactly that here. So all we're going to do is graph the x-intercepts and then see how it looks like. Okay. Now remember, f of x is technically z, according to our definition, right? It's the z on the outside. So now let's suppose we want to find the x-intercept. So that means I'm going to plug in 0 for y and 0 for z and just solve for x. So let's say, so we will find the x-intercept. So it'll be 0 is equal to 8 minus 4x 0. And then solving for x, we get x is equal to 2. So our x-intercept is 2, 0, 0. Doing the same thing for the y-intercept. So now plug 0 in for a z and x. So it's going to be 0 is equal to 8 minus 0 minus 2y. And then doing the same thing. So this is not in the middle. So solving for y gives you 4. So my y-intercept is 0, 4, 0. And then finally the z. So plugging in 0, 0 for x and y this time. So z is equal to just 8. Everything else is gone. So now how do we graph this? Okay. So remember, these are the positive, these are the positives, these are the positives respectively. And good thing they're all positive. So positive for 1, 2. So this is the x-intercept. 1, 2, 3, 4. And it goes up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's our solid. And it's actually perpendicular here all the way around. So this solid is generated basically by 3 different or 4 different triangles put together. This right side, left side, right side, bottom, and the side facing us. So it is this solid right here. Again, that's a nice quick way of sketching surfaces, or in this case, solids. So let's try one more. Now, everybody hates square roots, right? So why don't we just make this squared? And now we'll do the exact same thing. Find the x-intercepts. Okay. So first we'll find the x-intercept. So plug it in 0 full there. Does everyone agree? You get 4. Now the y-intercept, plug in 0 and 0. We get 0 is equal to 4 minus y, which means that's also 4. And then finally the z-intercept. That's all gone, so we just get 2 this time because it's the square root. So we take the square root of 4, gives you 2. Okay. All right, let's do the same thing. Yeah. All right, so same thing. So x is 1, 2, 3, 4. 1, 2, 3, 4. Z goes 2. Okay. Now, if anybody remembers back a couple portions, this is a circle. In fact, this is a half circle, and or a hemisphere, you want to call it that, right? So this actually looks like this. Where the height of this hemisphere is up to 2. It's a little bad drawing, but this is supposed to be going in the back here. So these points here crosses at -4, and these points way back here across it at -4 on the y scale. And it has a height of just 2. So let's see if I can draw a hemisphere a little nicer for you guys. So it's kind of looking like that, where these are now dashed in the back. As best I can do it. Okay. Now, why are we graphing this? Why are we sketching basic, I say basic, type of curves to deal with it? Well, the interesting part we're going to be dealing with pretty much, again, for the next chapter and a half, roughly, is something called level curves. And level curves all look like this. Now, these are more complicated, right? We're not going to be doing some crazy graphs like this on our own. These are computer generated. Okay? But as you could see, you know, that's a precursor of what we can do, right? We did basic ones, but this is what we can really do. And then the key thing you want to figure out is notice all of these lines going everywhere, right? Connecting all of these functions together. Now, one thing I want you to notice is, well, for example, here, that's a smaller distance than this, which is a smaller distance to that. And notice it gets gradually bigger and again gradually small again as we get back down. Right? You can kind of tell, you can see, emphasize it right here. This wave right here is much smaller than this one, which is smaller than that one, and it barely peaks, right? So it goes gradually smaller as these waves go up, or these weird lines going up in here, right? And I'm sure if you guys seen some textbooks with, or some books with like mountain ranges, it does the same thing, right? There's different like scalar going down, like different ridges. If you see it straight up, and when you straight down, you kind of see this kind of stuff going on. Okay. Now each individual line here. So this line right here, going all the way out and then back down, and every single one exactly like that is called a level curve. Okay. Now, a level curve is a function f of two variables and are curves with the equation f of x equals k, where k is a constant. Okay, and all of these things, what these level curves represent, is a way to mathematically show what's happening at every level as you go up and down of every type of wave. Because remember, all of this is applied into, if you see it in mountain ranges, exactly that. Right, this is most precise as a mountain range because it's like jaggeds going down. You can see like the Grand Canyon, you can see layers as you go up from down. Each individual level curve is different and unique itself. So therefore, each individual level curve has its own particular function. Hence why it's called f of x and y. Okay. So an example of a kind of a level curve, what's actually happening on this kind of stuff is, well, given a function in 3 dimensions, I'm going to try my best to graph this for you guys. Sorry that. And now at the very top, I have this level curve here, and it goes all the way around in a circle. All the way down. Well, the thing is, if I project this down to a flat surface, like a piece of paper, each of these individual level curves end up looking like a circle or an ellipse. Or again, for example, this level curve here, projected down is this one there. And this one way at the very top projects all the way down to the very first one. So this is where the value of k comes into play. Is k is a different value depending on the level curve you're at. Hence the reason why we have circles. So, remember the equation of a circle looks like this. So you can see this k value is basically r squared, the radius of the actual circle curve. Pretty cool. Pretty interesting stuff when it comes to this stuff. So that's the reason why, calculus is actually pretty crazy. Okay. Now, how do we read this kind of stuff? Okay. So here's an example of a level curve that's broken down already in 2 dimensions. Okay. And now we can estimate the distance, or we'll talk about distance, but we can estimate, let's just, the values of specific curves in the XY plane. So given all this information, let's estimate 4, 3. So what that's saying is, remember, this is x, y. So if x is 4 and y is 3, the point is right there. Okay, so remember, these level curves are all the same. So anywhere on this curve here is always going to be the value of 80. Anything on this curve here is going to be the value of 70, and so forth, 60, 50, and so forth on the other side. Okay. So since 4, 3 is exactly on the curve of 80, so we can estimate that 4, 3 is approximately or exactly 80. Or actually, wait, it's a little off, isn't it? Yeah, sorry, I'm looking down. My mistake. It's between 70 and 80. So it's approximately 75. My mistake. Approximately, right? It's not perfect. And we can do that for the other 2. So 1, 4 is right here. And this point is closest to the level curve of this one right here. And this has a value of 60. So we say maybe it's and now remember, you got to be very careful how you do approximation, because as I go this way, I get smaller. But as I go this way, I get larger because you're getting close to 70. So we could say it's approximately 62. Or 61, right? That's approximation. And then the last point, 4, 4. Okay. So 4, 4 is right here. Okay. So that's closest to the level curve of 70. And as I go this way, I get higher. So maybe it's approximately 71, give or take. Even 70 be, fine. It's almost exactly on the point. Okay. And later on in the course, we're going to be realizing, okay, just given this, because I am increasing, does that mean a minimum or maximum value? In other words, am I going to a steep, or is it going down to a valley like it is here? That's the interesting part, just by looking at the level curves themselves. So last part of this section is, well, how do we create level curves ourselves, or sketching level curves? Okay. All right, so given the function of this, we want to find the level curves of -3, 0, 3, and 6. Okay. All right, so just like normally we have, here's a function, right? So all we're going to do is now plug a k in for our equation. So remember, our equation is f of x of y is equal to k. So if k is equal to -3, all I'm going to do is plug in -3 and set it equal to the entire function. So bringing this over gives us -9. And now all we do is graph that. So you can graph it the normal ways. I'll just use the same process we did earlier, since we did intercepts I'll just quickly do intercepts. So plug it in 0 for y, we get that. Plug it in 0 for x, we get 9/2. So this line is 1, 2, 3. And this is 4.5, I believe. So right there. So this is the level curve when k is equal to -3. And we keep going the exact same way. So when k is equal to 0, we get -6 is equal to -3x minus 2y. So that's going to be k equals 0. Plug in 0 for that, we get 2. Plug in 0 for x, we get 3. So 2, 0, 3, 0. And we keep going. So when k is equal to 3, bring it over. Plug in 0, we get 1. Plug in 0, we get 3/2. K equals 3. And if k equals 6, we just get 0. So it just 0 is equal to -3x minus 2y. So it's just the origin. So those are the level curves of this function. Yep. And then the last example, this is a pretty cool one. It's kind of similar to what we just did earlier. Given the same thing, so I'm just going to go a little faster. And so if you plug in 0 in for k and solve for your x-intercepts, well, I'll just do this way. So you get, if you just square both sides, you just eventually get this. And I'll just rewrite it as, this is the same thing as -9, right? Yeah, 9 is equal to x squared plus y squared. So that ends up being just a circle with radius 3. So this is k equals 3. Or sorry, k equals 0. And you do the exact same thing, k equals 1. You square it, add it over, you get 10, or sorry, 8. So then you just have circle with radius square root of 8, which is like 2 radical 2. So somewhere right here. And you get closer and closer to the center, which is pretty cool. And you get the very closest one is when k is equal to 3, because you get 1 itself. Yeah. So this is the way to